Yes, so my name is Vinicius Vaz da Cruz. I'm a scientist at Helmholtz Centre Berlin at the Photon Science Division. And what we're investigating is the dynamics and properties of transition metal complexes, which are molecules that are composed of central metal atoms, such as iron, cobalt, chromium, and is surrounded by ligands, which are organic molecules. And we are investigating their photoreactivity, which means like the light-induced reactivity. So basically a molecule that doesn't do so much when it's in so-called its ground state, when it's just like in its normal state. But once you give it light or photons, it reacts, it does something. So that's the type of process which we're investigating with X-rays. So what it does is, like, once you excite the molecule, it triggers the release of a ligand. So suddenly this molecule, which is very stable, wants to get rid of one of its ligands. And once and this processing is also hindered by the solvent, because we do experiments in solution. So you have to imagine this molecule is in water, and water is really clusters around it, and it doesn't allow this to really dissociate. But eventually this escapes. And then a molecule from the solvents which can replace its ligand, and that's the reaction. Well, the capabilities at SCS, at XFEL, they are relatively unique, because you have basically is all about the time resolution. In one crucial aspect is the time resolution, because you can go to very, very short times, like unimaginably short, which is the natural time scale for the motion of the molecules. So like for the vibrational motion of the atoms inside the molecule, and that's the time resolution which you can achieve here, and you cannot achieve at other facilities. The second point is just the sheer intensity of the X-ray free electron laser, because the probe we're using has a very small amplitude. It's a very sophisticated spectroscopic technique, but it has a very small probability of taking place. So you really need a lot of X-ray light intensity to trigger and detect it. And then here you have the combination of both worlds, the excellent time resolution and the intensity to detect this process with the HRIC spectrometer. That's how we can detect the so-called resonant inelastic X-ray scattering signals. The other point is that they also have coupled, they have the SSE detector, which allows to also do a process which is a little less minute, let's say a process which is more efficient, which is just a difference in absorption. So RIX is a scattering process, and X-ray absorption is like a single photon process, and you can couple the two techniques to get a complete picture of the process. It all comes down to like fundamental basic understanding, because this is like this is a fundamental reaction step that takes place in many more complex systems. So if you're able to pinpoint the governing principles that for this type of reaction, you can provide valuable information for people trying to design better catalysts, better light absorbers for like photovoltaic applications, for instance. But we really focus very sharply on the fundamental aspect of how this ligand can be released, and what hinders it, what makes it efficient, so that we can generate the ground understanding for further technical applications relevant to society. Yeah. The experiment went excellent. It was. We had many hurdles and obstacles, but we overcame everything. Also with invaluable support from the SCS team, and we got exciting data, and we're really looking forward to working on it and analyzing and getting the information out. Yeah.